Movement is one thing, and everything in the universe moves. Circulation is more complicated. Circulation suggests movement in a mostly closed system. Think blood in your body, or the air in a jetliner at 30,000 feet. But it's really movement itself, the complex, endless travel along a closed path that defines circulation. One big, endless loop. Energy, gases, liquids, life. Circulation describes the world in motion. Here's a word: equilibrium. Equilibrium means a state where forces reach a balance. To illustrate, we're making a detour to Daisy World. No one lives here. Daisy World is a famous thought experiment. Imagine an ideal empty planet. In the early days, black daisies bloom first because they like cool temperatures. Black blossoms absorb a lot of sunlight. They have a low albedo, and as their population increases, the planet's temperature heats up. But white daisies like warm temperatures, and gradually their growing conditions improve. However, white flowers with a high albedo reflect sunlight back into space, which cools the planet, and you can guess what that means. Gradually, the sloop settles down and reaches a balance, equilibrium. White and black flower populations adapt to a changing world, while simultaneously changing the world they live in. In the real world, things are a little more complicated. There's always something knocking one part of the system out of balance, and that keeps everything in motion. But you're wondering, how does it work? The sun's energy gets things moving. Here's another idealized planet, and it's spinning. This one with an atmosphere. Sunlight warms the equator more than the poles. Heat always flows from warmer to colder, pursuing equilibrium. It's this planet's rotation, its spin, that sets up the forces to put everything in motion. Rotation prompts a phenomenon called the Coriolis effect, which sends straight paths into curves. Add land masses and clouds, and suddenly those easy spirals start spinning everywhere. Let's get back to Earth. Here's what global ocean currents look like near the surface, based on satellite observations and supercomputer calculations. Of course, we don't live in the perfected world of a computer. For millennia, humans have drawn maps of all types to help us get from place to place and to help understand where we are before setting out. Oceans run deep, and there's a powerful force driving circulation way, way down. As loops go, this one's a doozy and takes hundreds of years. This is Earth's conveyor belt, propelled by forces that change water density. It's called thermohaline circulation, thermo for temperature, haline for salt. The light arrows represent warmer, less dense water moving near the top of the ocean. The dark arrows represent colder, saltier, denser water crawling along Stygian depths. With densities always in flux, water endlessly moves higher and lower in the blue vastness of open ocean, pumping in slow motion. In this ascending-descending waltz, the whole world keeps moving. In our submarine, we rise, emerging into gentle trade winds and sloshing waves. Oceans and atmosphere meet each other at the endless horizon. So what do we have? We have sunlight warming some parts of the planet more than others. We have different densities of water on an enormous global conveyor belt. And of course, we have a rotating planet. So it should be no surprise to see a wide range of temperatures on the ocean's surface. Like this. And it's an absolute fact. Over long periods of time, ocean temperatures affect the atmosphere far more than the other way around. After all, oceans store more heat than the atmosphere. Energy in, energy out. Chemistry and sunlight. Wind and air and pressure, and we're off. Floating among an incalculable mass of water, now rising as gas into the sky. Water vapor evaporated from the surface of the sea condenses into clouds. Clouds grow and heave and release rain. The moving colored patches here show rainfall all over the world, measured from space. That moment when matter changes state from gas to liquid releases energy. And after sunlight, the transition from one physical state to another is the most efficient way to exchange energy. Rising warm air propels a powerful elevator through the air column. But as we've seen elsewhere, our rotating planet sends things spinning. And as it was in the ocean, the Coriolis effect sends atmosphere curling away from the equator. Air currents form spirals as they slide across the planet, churning the sky. If it were only that simple. So many forces affect winds, from the shape of mountains below to the density of clouds above, and much, much more. Even a computer model of global winds, a simulation about how we think the planet works, looks like so much wild spaghetti. But even in the seemingly tangled chaos, there are rules of order and explanations for everything. Everything connects to everything else. Where there's a difference in temperature, there's movement, and therefore circulation. Ocean currents, winds. When things heat up, they move. Remember our perfect planet, with a warm equator radiating out to cold poles in search of equilibrium? On Earth, that process has gone on for eons. There's never perfect equilibrium. There's always something destabilizing the system. Remember the daisies? Our future will also be shaped by destabilizing forces. But in your mind, look at that idea another way. Over time, there is a balance, a gradual give and take of natural forces. Across the ages, the planet finds averages, a rhythm and rhyme moving through time. It's an endless loop, and a beautiful one. And depending on how we choose to treat our planet will influence how well those loops stay in balance forever.